This lecture is about integral and differential forms of Faraday laws. In the last lecture, we have discussed in detail Faraday law of induction. Faraday law of induction is a very important law and it forms a bridge between electrostatic and magnetics and the conversion of electric and magnetic field, and that is why it is also a part of Maxwell equations. So it has to work with both forms, integral and differential. Today we will discuss how this law can be converted into integral and differential forms both. As it is seen, this is the syllabi of your unit, your fifth unit, last unit, and we have discussed first part electromagnetic induction, Faraday laws and electromotive force, and today we are dealing with this integral and differential forms. In this lecture, you will at the end of the lecture, you will able to learn significance of Faraday law of induction, its differential form, integral form, Maxwell Faraday equation, and conversion of from integral form to differential form. Faraday law of induction is a basic law of electromagnetism, which predicts how a magnetic field interacts with electric circuit to produce an electromagnetic force. This phenomena is called electromagnetic induction. A magnetic field interacts with circuit and produce a force. So we use this force as a fundamental operating principle of many devices, many arrangements like transformer, inductors, and many types of motors, generators, and solenoid. This is the fundamental of many devices we are using. Because using this electromagnetic force, we can perform many actions, many works. The Maxwell-Faraday equation describes the fact that spatially varying and also possibly time varying depending on how magnetic field varies. Electric field always accompanies a time varying magnetic field. What is the meaning of this? First thing is we have to understand these two things, spatially varying and time varying. Actually, anything which is varying in the system, electric field, magnetic field, or any wave, we have two types of variation. Spatially varying means something which is varying when it is moving in space, in x direction, y direction, or any direction. So that is called space. If something is moving and also varying, if something is have different value at different places, then it's called spatially varying. Space, varying in space. Time variation is also there. Even at the same place, wave may vary time with time. At the same place, we may have different values due to time variation. So, whether it is a spatially or a time, it depends on what type of magnetic field you have. But If we are having any specially varying electric field, then it always accompanies a time varying magnetic field. While Faraday law states that there is an electromagnetic force may defined as electromagnetic work done on a unit charge when it travels one round of conducting loop. On the conductive loop, electromotive force on a conducting loop when magnetic flux through the surface enclosed varies. When you vary the magnetic flux passing through this will create electromotive force. So both are similar, but the way is different. Main thing is magnetic flux should be vary, and change in magnetic flux result in induction or electromotive force. We have discussed Faraday law on the last term. However, many laws, many statements are there, but the most widespread version of the Faraday law is the electromotive force around a closed path is equal to negative of time rate of change of magnetic flux enclosed by the path. A magnetic field is there and flux is there. Now, the electromotive force if generated somewhere, then it is always proportional to rate of change of magnetic flux d phi by dt. Suppose phi is the flux, then change in flux is d phi with respect to time interval dt, then the electromotive force is always proportional to d phi over dt, and not only proportional but also negative. There is a minus sign. Minus sign means it opposes the direction from which it generated. The closed path here is in fact conductive path, we are saying. Here a Faraday experiment is shown. Faraday experiment showing induction between coil of the wires. The liquid battery on the right we have shown provide a current which flows through the small coils, creating a magnetic field. When the coils are stationary, no current is induced. But when small coil is moved, in or out of large coil, the magnetic flux through the large coil changes, and this induces a current. This current is detected by galvanometer. First, again try to learn this. Now I'm giving you a brief of this. What is this? This is a liquid battery I have shown here. This liquid battery provides a current to the system. Now you have two coils here. Where are the coils? These are the two coils. This one is small coil A and this one is your bigger coil B. Now, the liquid battery provides a current which flows through a small coil A. We have joined this here. You can show here. You can see it here. This battery is joined with small coil. When this is stationary, there is no magnetic field. no current is induced. But if you move this coil in or out, either you move in or you move here, in both the cases, the magnetic flux of coil changes. And as the magnetic flux of large coil changes, this will induce a current. And how we are checking the current? Yes, we are checking the current through this galvanometer. This galvanometer is placed here. So this can be done. So electromagnetic induction or induction is a process in which a conductor is put in a particular position and magnetic field keeps varying or magnetic field is stationary and conductor is varying. We have shown here either you are pushing your magnetic field inside or outside, or you are also having a current flowing in this. So flux is changing and you are getting the results. Now we are learning how we can convert our integral equation to differential form. We know the Faraday equation in integral form. This portion is rate of change of flux. We have discussed this, and this is equal to the electromotive force for a coil, which is equal to E dot dl. Now, if this is there, then you can apply here Stokes theorem. We know from the Stokes theorem the line integral is always equal to the surface integral del dot v dot ds. If we calculate on the line integral, then it is always equal to the surface integral of the same curl of that quantity. So using this, we can convert our ruled convert our equation in this, or better to write like this. Now replacing the right hand side using previous equation 1, you can write this surface integral of del cross E should be equal to del phi by del t. We know this. The flux can be done as B dot dA. So if we replace this d phi by dt, phi b and d phi by dt by this, so this can be done as equation like this. Yes, we have used same area, that is why we have converted dA into ds. So both are here. So finally, del cross E is equal to del B over del T. And this is called the Faraday law in differential form. So again you can revise this, but it's very easy. First is take the Faraday law in integral form, then apply Stokes law to convert line integral to surface integral, then convert your flux to in terms of magnetic field again on a surface integral. If both are surface integral, you will get this equation. This gives the idea of Faraday law in differential form. You may ask why you need differential equation and integral equation both. Sometime in the time of calculation, sometimes the calculation is easy in differential form, and sometimes the calculation is simpler in integral form. So we have introduced both. And the another thing which is important is it is one of the equation of Maxwell, and Maxwell we use in both forms, integral, differential. So this part is very important to learn how to get differential and integral form. In this form, del V over del T is called rate of change of magnetic flux density vector, rate of change of magnetic flux, del V over del T. On the left hand side, E is the electric field, and del cross operator means we are taking here curl, how the field is curling about this. In this lecture, we have discussed Faraday law of induction in differential and integral form, and we have discussed how we can convert one form to another form, integral form to differential form, and why it is necessary, why it is important. In the next lecture, we will study self-inductance and mutual inductance. Thanks and take care.